Suppose you want to find the area under y is equal to x squared from 0 to 1. And to do so, we'll be using bunch of rectangles. How many though? Technically, we want infinitely many, but before we can do that, we need a formula. Suppose we have n many rectangles, and we are going to do it with equal widths. So let's just make some cuts. You can imagine n is equal to 10, then each one will just be 1 over 10. Again, equal width. But we want n, so this is 1 over n. The next one is 2 over n, and so on, so on, so on. And the last one is 1, which is n over n. Now, I'm going to use this as my x value, go up, hit the curve, and then go to the left, and create my rectangle like this. Let's find the area of this first rectangle right here. The base is 1 over n, and then the height, well, we use this as the x value. If I plug that into here, I can get the y value, which will give us the height. And that will be 1 over n here, and then you square that. That will give us the height. For the next one, we'll be using this as the x value. Go up, hit the curve, and then go to left, but do not go all the way to the y-axis, just the end of this interval here, and then you will have our second rectangle. The area for that is once again the bottom right here is 1 over n. So let's go ahead and add it together with that. And the height is, plugging this into the x, we can get the y. So we have 2 over n squared, and so on, so on, so on, until the very last one. Use this as the x value, go up, hit the curve, go to the left, and then come back down. We have the rectangle. The area is 1 over n times the y is n over n squared. This is the general formula when we have n many rectangles, equal width. Now, we want infinitely many. That is to take the limit as n going to infinity. Very nice, huh? Next, I'm just going to do some algebra with this. This right here is just the limit as n goes to infinity. I will first factor the 1 over n from every term. And then we will have this right here, right? 1 over n squared plus 2 over n squared plus 3 over n squared, and so on, so on, so on. And the last one, n over n squared. Now, this is a lot to write, isn't it? Yes, it is, because there are so many additions and all that. However, do notice that we have 1, 2, 3, 4, all the way to n. These are the only things that are changing. So, we can actually use a summation to help us out to write this in a more compact way. Check this out. I'm still going to keep the 1 over n right here, but for all this part, I will put them in the summation, which is the sigma right here. Let's use I for the index, and it starts at 1, and then ends at n. The only thing that are changing is this, so that will be the I, and the rest stay the same. So this is equivalent as that, it's the same as the original. Now we're almost there, but what I want to do is, traditionally, I will put this at the end. It's okay, right? Because earlier I have 1 over n times this quantity. Of course, I could have put the 1 over n at the end as well. So let me just write this down as the limit as n goes to infinity. The summation first. I goes from 1 to n, and then I over n squared, and then times 1 over n. Okay, now let me explain this right here real quick. This right here is a Greek letter called the sigma. Not the sigma that you guys see on TikTok or Instagram. This is the actual sigma. In fact, this is the capital letter sigma. There's also a lowercase sigma as well. The reason that we use sigma is because we're talking about the sum. So just think about this as the sum. Now, ladies and gentlemen, this right here is a sum, but it's a concrete case, meaning whole numbers. N has to be 17 or 25 or 1000, all that stuff. let me introduce you guys the super version of the summation called the integration. If you look at S, just write S, and I'm going to stretch it vertically, it will look like this. This is a super version of the summation. Of course, it's called the integral. And when you are doing an action to it, you are integrating something. And when you're integrating something, that means you put things together. So, what is the integral though? It's this right here. Have a look, ladies and gentlemen. The limit as n goes to infinity of this summation, this part, just think about that as the integral. And what's this part? Well, that's our function, isn't it? Yes, you can write this as x squared. Right? That's our function. And now what's 1 over n? That's the width of each rectangle. What I'm going to do is, I'm going to write that as dx. Once again, this right here corresponds to this sign or symbol. This right here is our function, write that as x squared. And this right here is the width of each rectangle. Write it as dx, which stands for a small change in dx. Because imagine, if n is 1 million, 1 over a million is extremely small. It's really, really skinny rectangle. Dx, just a little bit. Yes, and in fact, if you want to find the area from 0 to 1, all you have to do is integrating this from 0 to 1. And then to do this integral, you just add 1 to the power, because you have to do the reverse power rule, because you are doing the antiderivative for this. And then divided by the new power, which is divided by 3. So you get 1/3 x cubed, and then you go from 0 to 1, plugging 1, and then plugging 0, and you get 1/3. Let me write it. You plug in 1, you have 1/3 times 1 cubed. That's the first part. Minus, you plug in 0. But this part is 0, and that will give you 1/3. That's how we end up with 1/3 for the answer. But the connection is this gives you the integral, this gives you the function, and this gives you the dx.